Hi all, Dr. Clark here again, and today what I'm going to show you is a demo of how to make both exponential graphs or do an exponential figure and a logistic figure, and how to do it in Excel fairly quickly and without a lot of, I guess, without a lot of pre-notation or a lot of knowledge on inputting a bunch of functions and things like that. They're really simple functions, really easy to do, and it'll help you guys with your homework. And if you've already completed it, it'll help you understand how to do it at a later setting. Okay, so let's first look at something like an exponential growth. Remember, exponential growth is just growth, or G is equal to R times N. So here I can change this to read exactly that. G is equal to R times N. Okay, and so if hypothetically, if we're starting with a population of 10 individuals and we have a growth rate of 0.25, or a quarter of the population is going to reproduce a single individual. Then you know that the growth in a given time, let's say it's years, okay, you know the growth is going to be 2.5 individuals. Okay, so I can come down to the second year and I can just type equals. Okay, and what I want to do is I want to add the first year's growth plus, or the initial growth plus whatever was added that first year, which is going to be this column. Okay, by doing that, I can calculate my new population. So this is population of year 2. This hypothetical example is basically telling us that R is the same no matter what the year is. Okay? It's always the same, quarter of the population. Okay? N is not going to be the same, but I can drag this down also, and I'll show you that it'll calculate itself in a second. Okay, because here my G is going to be N times the rate of growth. Okay? And so when I drag this down, it will change everything. So you can see the population growth starts out fairly slow. Remember, that's that initial period. And then you have exponential growth, and it really starts to grow extremely fast. Okay. Now, like I said before, eventually this will reach a carrying capacity, which I'll show you over here. Carrying capacity come into effect. But if there's no carrying capacity, or the environment has enough food resources, enough resources as habitat and whatnot, then you can expect the population to explode, and like this one does. So to graph this is really simple. We want to graph what the population is and the year of the population. Okay, and so if we jump over here to insert, and to do this we want to insert a scatter graph. Okay, and so see here, you can see it starts off really slow, kind of in that lag period, and then exponential growth, and you get this point, and it will just keep going up and up. And to see this, if you're interested in that, I can just drag this out. So let's say I'm not going to stop at 20 years. Let's say I'm going to stop at 50 years. Okay, and so if I jump back up here, and I can drag these 3 columns, drag them out to 50. Okay, and now you can see the population is huge. Oh, actually, I can't do that. Here, let me correct that. So what I want to do is I want to drag this one. So what that did is Excel adds when you select something, it will often add to it So it added to my rate of growth. Instead of keeping it as 0.25, it started adding to it. So the rate of growth really changed a lot. Okay, that should have corrected it, but just to make sure, I'll select this column and drag it down also. Okay, so now instead of having this graph stop at 700, if I go into the chart and I say select data, then I can just select the data that I'm actually interested in by editing this, and I can select the X variables. X variables, remember, are independent variables, so the year really makes no difference, and it's not going to determine what your rate of growth is for a given individual. Or I'm sorry, the number of individuals reproduced in a given year is not going to tell you that it's 1980. Okay, so that's independent. Your dependent variable does depend on the year, and so we want our population to be the dependent variable. And you can see when we do that, hit OK, now you can see that this graph has changed quite a bit. Huge lag period and then a massive takeoff, giving you that J-shaped exponential growth. Now, again, eventually K will be reached. And so if I jump over here to this example, and now we're talking about logistic growth, okay, you can see I start same 10 individuals, rate of growth is 0.25. Same thing. In the first year, it's going to be 2.25. Okay. Let's say my K is 100. So what I've done here, if you look up here, H2, that's your rate of growth, times G2, or your original population, times K minus N, okay? And so I'm saying that the population's carrying capacity is 100, okay? So minus G2 divided by K. And so if we go down here, same thing as before. This is equal to the original population plus that year, okay? And so these two look identical, but now you'll see that as we start progressing and the population gets close to that K, the rate of growth is going to decrease. Okay, so I'm going to drag this one all the way down. Okay, remember that your population can increase at 0.25 no matter when. Okay, and then I'm going to drag this one down to 50 years. And then if I come back up and recalculate the population, now you'll see what occurs when you have a K, a carrying capacity. So now that I have a carrying capacity, you can see at about 28, 29 years, the population has reached close to 100, okay? But it's not going to break 100 because as your population gets close to K, your rate of growth decreases. Okay, so the number of individuals that you're actually adding to the population pretty much goes to zero. And so you can see that even way up here, we're only adding, a half an individual by, 24 years or whatever that time period is. So you can see when we plot this, you'll definitely see that transition from the lag period to the exponential period to the stationary phase. And so let's plot this one out. Same deal, I can just select the data. I go over to insert. I want to select a scatter plot, and there you can see starts off fairly slow. Now I can change the dimensions of the graph so you can see that a little bit easier. So if I format my axis and tell it to increase units by 1, then then it should have worked. Yeah, so I'll just have to drag the graph out a little bit for that to occur. Okay, so you can see that it's, taking quite a few years before you even get to 20 individuals, starting with 10. Okay, it takes almost 5 years to get to 20. Let's see. Yeah, so 10, 12, 14, 18. Yeah, year 5 is when you break 20. Okay, so that's that lag phase. Then exponential. Okay, so going, from year 5 to year 10, you've doubled your population. 10 to 20, okay, you've more than doubled your population. Okay? But now you're reaching that close to that carrying capacity. So now you get that those points are reaching carrying capacity, K is getting close to N, or N's getting close to K, and you just sitting there. Now remember that in real populations, the population rarely sits right at K. Okay, a lot of times it'll bounce over it, which will cause too many births, not enough deaths, so you'll get this backtracking, you'll lose population, it'll come back down, and it'll go back and forth around K. Sometimes populations stay just below K and bounce up and down. Okay? It just depends on what the carrying capacity is. What is determining it? Is it determined by, the habitat available, the number of nesting sites, the amount of water, or is it food, or what's determining K, or is it a multitude of those factors that determine K? Okay, so again, K is not just a set point where it's like, oh, exactly 100, that's it, and that population will sit right at 100. Okay, that's not necessarily true. It'll oftentimes bounce above it, which will cause it to crash down because, the habitat is limited to about 100 individuals. Okay, and so if it bounces up and there's not enough food, then you'll see some starvation, and that'll cause it to crash, or overeating, and whatever the resource is that they took out of the population will cause maybe a new K. So maybe if it's overeating, okay, and the new K is 80 the next year or the next couple of years, then you'll see that population crash. And so K can bounce around for sure because it just depends on what's determining K. Is it the amount of trees? Is it the amount of water, grasslands, food? Is the amount of predators in the environment? This can all be determined, okay? But that should give you an example, a pretty quick example of how you can create a exponential growth curve, okay, and a logistic growth curve. So remember, an exponential growth curve, there's no carrying capacity. Okay? It can be added and would be added at some point in time. And then logistic growth curve, there is a carrying capacity, or K. So that population would stop. Okay? I hope that helps. And if you have questions, of course, always contact me.